Welcome to the course on fatigue and fracture. We start with the question, what is fracture? Now, before I go into answering that question, um, let me draw your attention to this particular paper, which was published by a person called Alan Arnold Griffith, who was an engineer with the Royal Air Force establishment in England. And the paper was titled The Phenomena of Rupture and Flow in Solids, published in the Philosophical Transactions. I would draw your attention to the year it was published. It's 1921. And in some ways, this paper forms the cornerstone, from the foundation of what we are going to study in this course. So in some ways, this is the 100th year of fracture mechanics, and you are studying fracture mechanics in its 100th year, which is a fact I thought I should mention to you at the very onset. Now, Griffith's idea of fracture was based on very simple premises. Now imagine you have a uniaxial, you are conducting a uniaxial tension test where you are applying a force in the axial direction to a bar which is very long in one direction, and the cross section of the bar is small compared to its length. The cross sectional dimensions are small compared to its length. Now when the bar, so under the application of this force, the bar will deform, bar will elongate, and it will elongate in such a way that its total potential energy is a minimum. Now, uh, Griffith suggested that this bar, instead of deforming, may form a crack if the energy required to form a crack is less than the energy required to deform it without forming a crack. Now, energy required to form a crack means a crack is two new surfaces that have to come up inside the material. So, formation of these two new surfaces requires some energy. So, the energy required to form these two surfaces has to be less than the energy required to deform, in order that the crack can be formed. So his explanation was an energetic explanation, which said that it is energetically favorable for a material to form a crack than spend energy in deforming without forming a crack. If that is the situation, then a crack will pop up inside the material. This is the basic understanding even today, that a crack will form whenever it is energetically favorable for it to form, whenever the energy required to form the two new surfaces that the crack involves uh, is less than the energy required to deform the material, deform the structure. So, um, in fracture mechanics, we deal with a few basic questions. And these basic questions rely on the assumption that every structure has defects of different sizes present in it. You do not have structures which do not have defects. However small they might be, there are defects all over the structure. So this is the basic design principle that uh, that design by fracture is based on. Now, the question is, of all the cracks that exist in the structure, will one grow catastrophically, or will all the cracks remain dormant? If all the cracks remain dormant, I don't really care, because it's not going to fail the structure. But if there is one crack in some location which is able to grow catastrophically, then then my structure fails, and I have to be wary of that situation. Uh, so if it happens that there is one critical crack in the structure which can grow catastrophically, then I have to further ask the question, how fast will it grow? And will it keep growing, or will it stop? So fracture mechanics actually answers these three, or tries to answer these three questions. Given a set of cracks, fracture mechanics can tell you whether one or more of those cracks will grow. It can also tell you how fast it will grow, and it can help you design strategies that can be used to stop it from growing. Okay. uh, what you will see here is that fracture mechanics basically assumes that defects or cracks already pre-existing in the structure. So defects and cracks are always present in the structure, and fracture mechanics does not question how those defects came about. So to begin this course, I thought I should give you some idea of how these defects on which we are going to apply our fracture mechanics, how these defects can come about. What I'm going to say is not exhaustive, it's not everything, but these are some of the important ways in which defects appear in structures. So some defects would appear during operation. Some defects appear during operation, and one of the ways in which defects do appear is through fatigue. Fatigue leads to development of large defects from small defects over a very long period of time, over a very long period of operation. So this is the cross section of a shaft, and as you can see that this shaft had for some reason a small initial flaw. So this was the initial flaw, and then as the shaft was being used, it grew by a little bit every time the shaft was operated. And these marks that you see here, very closely spaced, you can hardly see them. These marks are called striation marks, which indicate every step the crack was taking as the shaft was being operated. So this took place over a very long period of time, and then led to a crack which then grew probably catastrophically and led to failure of the shaft. So fatigue is one major source. Fatigue or long operations over cyclic loading is one of the major sources of the initial defects that ultimately lead to failure of structures. The second major source is our aggressive environments. So there are various kinds of aggressive environments that materials may be subjected to. So this is one example where you see this is part of a oil pipeline. So this is part of an oil pipeline where you see this is the crack that has ruptured the pipe. And if you look closely at this part under a microscope, you see the grains in the material. I hope you know what the grains are. So this in this material, these are the grains. So this is, for example, one grain, and you can see that the intergranular boundaries, these parts, the intergranular boundaries, they have cracked, and they have actually cracked because of the hydrocarbon that was flowing through the pipe that leads to infusion of hydrogen into the steel of the pipe material, and this hydrogen reacts with certain elements in the steel and leads to what is known as hydrogen embrittlement, which is basically a weakening of the grain boundaries, and that leads to small defects which grow and finally lead to a crack of the sort. Another um, example of aggressive environment is corrosion, which happens in say saline environment. This is a corrosion um, due to ingress of chloride into an aluminium structure. So what you see here, this whole kind of feature that you see here is actually the top view of this corrosion pit that had somehow developed in the material due to ingress of chloride. So this was result of a chemical reaction that took place, created the small pit, and then during operation a crack emanates from the small pit and leads to failure of the structure. So as I have already mentioned, we are not going to study how this kind of initial failure, initial defect forms or this kind of an initial defect forms. We are not going to study that. What we are going to study is, given that these kinds of defects exist in the material, will one of the defects grow and lead to complete failure? Will it lead to a growing crack? That's what we are going to study. But it is important to understand how these initial defects might actually come about. So another source of the initial defect is excessive deformation, and one of the major one of the very celebrated examples of this, you might have already seen in your undergraduate days. You must have done a uniaxial stress strain test with a dog bone specimen, which looks like this. So this is how the specimen looks like, and then you pull it with forces at the two ends, and it starts necking somewhere in the middle. So this is the neck, and then it cracks along the neck, it breaks along the neck. And this is the experiment that every undergraduate student does in order to measure the stress strain curve, in order to get obtain the stress strain curve of steel or aluminum or something. So of some ductile material. Now if you look at this neck part carefully, you will see that the two parts form what is known as a cup and a cone. So this part can form the cup, which is actually a depression, okay, and this part forms the cone, which is actually a small hill. So these two fit together. Now if you look at the top view, if you look from here under a microscope, if you look at a small area here, what you will see is a structure like this. This is a typical example of dimpled structure, which is very typical of I will show you another example of such kind of a structure, which is another example, which is a hallmark of ductile failure. So this is a ductile material, steel, aluminum, copper, and this is a typical close-up of a cup and cone fracture. If you looked at the cone, you looked at the cone. If you looked at the cup, if you looked here, you would see more or less a similar kind of picture. Now, people have looked at these. So this is these are actually signs of early defects that caused the failure. People have looked at this. So what people have done is taken a dog bone, pulled it to some extent, cut it across and looked at the surface, then taken another one, pulled it some more, cut it, look at the surface, and doing this they have pieced together how this particular process happens. And this particular process actually happens along this route. So you have the start of necking, which is an instability phenomena. You have a start of necking in this region. So you're pulling like this. When it starts to neck in this region, the stresses are very high in this region, which gives rise to microscopic voids. These are very small voids. Then some of these voids, which are actually represented by these dimples. So these dimples are depressions. The black parts are away from you, the white parts are towards you. So you can imagine this is like half of a sphere, half of a hollow sphere, and the other half of this hollow sphere would be somewhere on this surface. So these two would fit to form a complete sphere, which are the signatures of these voids that have formed. Then some of these voids might coalesce to form a bigger defect, and then this bigger defect, if it's big enough, can grow, can propagate. That's where my fracture mechanics comes in and cause failure here. So this is the initial defect from which fracture mechanics would start to operate, but this defect comes by through the formation of voids, void nucleation, then void grow, then voids coalesce, and finally a large enough coalesced void would propagate to form a crack which will lead to failure. So these are some of the normal expected ways in which the initial defect can come about. It can be through aggressive environments, through fatigue, and as well as through excessive deformation. Now, there are some inadvertent ways in which the defects come about, and they have to deal with, okay, I'll come back to this later, and they have to deal with poor design and manufacturing processes. So, your design may have stress concentrators, which would be regions of very high stress where defects can form. Poor material selection might lead to defects. Defects may be induced by the manufacturing process itself, cutting or forging or improper heat treatment, and defect may also result from faulty assembly of components. So these are some of the inadvertent ways in which you can introduce defects in a structure. And uh, let's look at a case study which is taken from this paper, and this is on the axle of uh, uh, railway. So um, we need to know, as I said, that what is the size of the defect that we will start from. We need to know the size of the defect that we start from. We are not going to look into how the defect came about, but we need to know that what size of initial defect are we going to consider. Now, the size of the initial defect will be determined by, and this is a design practice, it will be determined by the smallest size that you can detect with the inspection methods that you have at your disposal. For example, in this example, railway application example, uh, these are some of the processes. You don't need to really worry about what these processes actually do. These are some of the processes by which you detect cracks in a structure. So you have these railway axles, wheel axle assemblies, and there you use one of these methods to detect whether it has a crack or not. And each of these methods will have a resolution. That means there would be a smallest size of the defect that it can reliably detect. For example, if you take ultrasonic testing, then the probability of detection is almost 1 once the crack size reaches a depth of about 6 millimeters. So anything above 6 millimeters would be definitely detected if you are doing ultrasonic testing. Now, in that case, when I do a fracture mechanics based design, I should always assume that there are defects of the size equal to or less than 6 millimeters in the structure. So the starting point of my fracture based design. If I do something better, like magnetic particle detection, if I do this, then I have a 100% probability of detection if my crack is, say, like 3 millimeters. And in that case, I have to assume that the structure always has cracks of the size 3 millimeters or less in it. And then I have to ask those 4 questions, whether these cracks can grow, how fast they will grow, whether they can be stopped, and so on. In conventional design that we have learned in our undergraduate days, uh, the basic premise is that we have to design in such a way that everywhere in the stresses at any point in a component does not exceed the yield stress. So stresses cannot exceed the yield stress or some combination of stress like the von Mises stress or the Tresca stress based on some criteria should not exceed the yield stress. Fracture mechanics based design asks a different question. The fracture mechanics based design asks if, assuming that there are defects in the structure, is there a defect what is the load at which this defect will start to grow. That is my limiting load. Whereas in engineering, conventional engineering design, which is also called yield based design, uh, the load should be such that it does not cause yielding at any point in the structure. So these are two different concepts, and over the years, many ways of designing things with fracture mechanics have been devised. So the first is the safe life concept, which says that okay, cracks do exist in the material, so you have to design so that you limit your loads for very long life. So it's a bit like the concept of endurance limit. So this is the stress range. This is the range of stress that you're going to apply, and this is the crack length. This is the size of the crack that exists in your structure. So uh, if, for example, your detectability limit tells you that the cracks are of this size, then fracture will not happen, and your material, your structure will fail according to the concepts of fatigue and yield at the endurance limit of the material. So this will fail at the endurance limit of the material. If your crack lengths are of this size, if your crack lengths are here, then uh, it will fail under linear elastic conditions. That is what we are going to learn next. LEFM means linear elastic fracture mechanics. So it will fail in this region. It will fail without causing much plasticity in the material. It will fail according to linear elastic fracture mechanics conditions. But that you see is much lower than the endurance limit. For the endurance limit to be valid, so for the material to fail by yield, your crack lengths have to be smaller than this. If your crack lengths are bigger than this, you will fail by fracture, but fracture will not cause much plasticity. Whereas if your crack lengths are in this region, you will cause, again, fail by fracture, but you will cause EPFM, or EPFM will come into the picture, or elastoplastic fracture mechanics will come into the picture, and your crack propagation uh, during failure will cause a lot of plasticity. So even here, the stresses that you can use in the structure are lower than what you would do for endurance limit. So if your crack lengths, if your detectability limit is in greater than this, then fracture mechanics will come into the picture, and you will have failure by fracture rather than failure by yield. Okay, so if your detectability limit is to the right of P, then you will have to limit your stresses to this region. If you don't want plasticity to happen while the crack is propagating, then you have to limit your stresses in the structure to this region. Okay, so apparently if you do this, the cracks will never grow, and you will have infinite or close to infinite life. This is not always possible. You cannot always limit your load ranges, and so the other concept is a fail-safe concept. So the fail-safe concept suggests that you design such that cracks, of course cracks are there, small cracks are there below my detectability limit. Let them also grow, but let them grow in a manner so that timely corrective action is possible. In other words, let the cracks grow in a manner that so that they grow slow enough so that I can detect them and take corrective action. So this is the concept of fail-safe design, fail-safe fracture-based design. Another variant of that is again that okay, small cracks are there, they also grow, but whenever they try to grow, I sort of guess where they are trying to grow from, and then I try to arrest the crack. I try to stop the crack from growing before they cause complete fracture. And this I can do by one, modifying the material that I'm going to use, and by also by clever design of the structures, by adding what is known as crack arresters, which are there in several structures that you see around you. So these are the three major concepts of design based on fracture. There's of course another brute force kind of a concept, which is damage tolerant concept. So you say that you do nothing, but you just do routine maintenance tests, overload tests, and remove cracks as when you see them. You either patch them up or fill them with something whenever you see them. So this is kind of a brute force approach, which we are not going to talk about much, but a lot of the industry probably uses this. But we are not going to talk about this. So our our concepts would be like uh, fail-safe concept to, so how can we limit our loads so that cracks never grow. Sorry, that's the safe life concept, limiting our loads so that cracks in the structure never grow. Fail-safe concept is uh, we don't do anything of that sort, but we ensure that the cracks grow slowly so that we can take timely corrective action. Or we modify our structure to add crack arresters, or we modify our material to be crack growth resistant so that the cracks get arrested soon after they start to grow. So so let's see an example of how a fail safe a safe life concept works. So this is an example of a safe life design, and this is for, again, for an axle, a wheel axle assembly in uh, high speed trains. So this is your wheel. This is part of the half of the wheel, as you can see, and sorry, and this is the hollow axle. This is the axle. It runs across the compartment, and this is hollow here. Now, uh, what a safe life design would do is, uh, first step would be to identify the typical locations where cracks appear during operation. So this is basically from experience. You can also do numerical calculations to figure out where these cracks appear, which are the most likely places. But from experience, these are the likely places. These are the likely places where cracks are mostly seen. So what you need to do is, um, starting from these likely places, you model the axle. This is the model of the hollow axle, and here I start with a small crack. Here I start with a small semi-elliptical crack. This is my starting crack, which has a major and minor axis of C naught and A naught. These are two quantities that are defined by my detectability limit. If my detectability limit is like 6 millimeters, like in ultrasonic testing, then A naught is 6 millimeters, and 2 C naught is something that is again given by the method by which I'm detecting the cracks. So I start with this crack, and then I try to model how this crack grows through the material till it reaches the inner periphery, so that it becomes visible if I look in this direction. If I look in this direction, the crack becomes visible. So how much time does it take to go through this thickness? If the initial crack size is this, and the initial location is as determined by my experience with axles. Now I can do this to wheels as well, and so the second step is to model them with initial sizes below the detectability limit. The next step is to consider physical conditions that the crack might be subjected to during operation. So let us shift from an axle crack to a crack in the wheel. So if you look at a wheel, the wheel is subjected to huge temperature rises whenever the train brakes. This is a high-speed train, remember. So whenever it brakes, the temperature at the contact between the wheel and the rail that increases tremendously. So these go up to 400, 500 degrees centigrade, and this actually has to be taken into account. This is an operating condition that happens for a short duration of time during braking, but this has to be taken into account in case of designing the wheel. So this happens, remember, at the rim of the wheel where the wheel comes in contact with the rail. So you do some kind of analysis, maybe a finite element analysis or something, to figure out that if you are supplied this kind of a friction force as it does in case of a braking, what is the temperature distribution in the wheel. And what you see is this is the rim of the wheel. This is the part that sits on the rail. So the rail comes somewhere here. So this is the rail. It's upside down actually. So at this location, whenever it breaks, you see the maximum temperatures are attained here. So this is the region where you must put your cracks, because this is the region where the largest amount of thermal expansion would take place. So once you have learned this, then you put cracks on different parts of the rim. So you put cracks here, here, here. These are different kinds of cracks, but are all semi-elliptical cracks. And then you study how each of these cracks are going to grow. And this is the last step in the design. And this is step 4. You try to figure out how these cracks grow. For example, this is a wheel that has a rim crack that is here and is growing inwards. Okay, so I need to know when does it reach the inner hub. Okay, to do that, this is another view of this. This is the crack after it has reached the inner hub, and when you what you try to do is do a calculation like this. So this is a crack which started from here. So this is again a semi-elliptical crack from this location, which is called the tread location, which comes in contact with the rail and has a very high temperature. So you put in this temperature rise and the frequency of braking, etc., and then you try to see how this crack grows, and we come up with these kinds of diagrams. So this is the number of cycles. This should remind you of your fatigue diagrams, SN curves, and so on. But this is different from SN curves. It tells you from calculations how these dimensions, initial dimensions, which are at the detectability limit at the beginning, how these dimensions are going to this dimension and this dimension A are going to grow as the number of cycles of braking increases. How many braking cycles is it going to endure? So these are for different wheels, but these curves tell you that how many cycles of braking can you sustain before A and C become so large that catastrophic fracture is going to happen. So this is how a fracture-based design would go. I have outlined the steps. Each of the steps are difficult to do and may be best done in a numerical manner, but we will leave it at that. We will learn learn a bit about how to handle each of these steps in the course of this what we are going to learn here. And let me turn to a slightly different topic, which is fractography. So this is again something that we are not going to talk about much later. there's a lot of post-mortem that you can do on uh, on broken surfaces. So broken surfaces actually tell us a lot, and there's a science behind it, which is called fractography. Fractography is basically the science of reading fracture surfaces, which is a post-mortem technique. So you might want to investigate why a particular failure happened by looking at the broken pieces, and you can make a bit of progress using the science of fractography. So this is a sample. This is from our own work. This is a sample which from the side view looked like this. So it was a block of rectangular block of material with a crack here. This crack was put in deliberately, and this was loaded in with two forces in this manner. And what you are seeing here, and this crack propagated and broke the surface, broke the whole structure into two pieces, and then you are looking at one piece from this direction. And here is this pre-crack that you had. This is the initial crack that you had, which is this, right? And then this crack started to grow, and here you will see is a part of the surface. This is looked at under a microscope. Here is a part of the surface that looks different from the others. So uh, the, you surmise that this is where the crack first started to grow. Then it grew very fast all over the place, but this is probably where the first move took place. It might have also taken place here. It might have also taken place here. So the crack started to move. This was the crack front, long one. It started to move like this. This was the point of crack initiation, and then this gives you a clue that you have to look at these locations to figure out the reasons for this failure. Okay. uh, this is again low carbon iron ductile material, and this is something that we have seen before in the cup cone fracture. We saw these dimpled surfaces. So this is one of the, this is either the cup or the cone, I don't know which, and it has these dimple surfaces, and it shows this is again a fractographic surface. Of course, looking at the dimple surface, you know that it's ductile failure. But if you look closely, you would see that these void or this semi void, other half is in the other piece. This semi void has something inside it. Something inside it. This is a this is a second phase particle, and you can analyze this and see that this is probably a FeO particle. This is probably a FeO particle, which are things that are added to the iron, to the steel while it's being made to improve its properties this way and that. And that tells you that these dimples, these voids that form, are forming due to decohesion of the iron from the second phase particles that are added to improve its properties. So while you are improving its properties by adding these second phase particles, you're improving corrosion resistance and so on and so forth. You are also making it susceptible to formation of these dimples, which can then coalesce uh, to form a bigger void, and then that void can grow catastrophically and lead to failure. So you are improving the properties, improving certain properties by adding these second phase particles, but you are also subjecting the material to the risk of failure by crack propagation. And these can be different kinds of things. Carbides are added. Cementite is a common constituent of steel. It can be inclusions like manganese sulfide. Manganese is added. Oxides like FeO that you see here, and all these dimples, therefore we know, are uh, are results of decohesion from these second phase particles. So the iron decoheses from the second phase particles and leads to these voids. which finally lead to failure. So fractography actually tells us a lot about how, what are the micro mechanics, what is the mechanics at a very very small length scale. You can see the length scale here. The length scale of this picture is 200 microns, which is visible here. So this length is 200 microns. This is even smaller. So these are very microscopic length scales. At these microscopic length scales, what is happening to cause the fracture is sometimes revealed by fractography. So this clearly tells you that these are intergranular failures. So if you have grains in the material that are shaped like this, these are rough grain shapes. And then intergranular fracture means, like we saw for the hydrogen embrittlement case, so this is typical case of intergranular fracture, where the cracks always propagate along the boundaries of the grains. So if you have intergranular fractures, then one of the surfaces would bear the signature of the grain boundaries. Well, both surfaces would bear signatures of the grain boundaries, because the crack is growing, say, like this, and taking whole grains out. So these are those signatures. So when the crack surface is uh, full of depressions or cavities which are of the size of the grains, then you know, with clean grain facets on the surface, you know that it's intergranular fracture that has happened. Uh, this is a typical brittle fracture in a alloy steel. So fractography, you are again looking at the broken surface from the top. So what you see here is a clean surface. This is the part where it's a clean surface, and you can barely see, but they're present. You can see the marks of striation around this. So these are the steps that fatigue crack has taken, but these are very, very, these are not very tall, so you can barely see them at this resolution. It looks like a clean surface, but here, so this is the crack front. So the crack is propagating in this direction, and first it propagates by fatigue, which leads to a relatively clean surface. Then you have a messy surface here, and this messy surface at higher magnification looks like this. Look at the scale again. The scale is 50 microns, so this length is 50 microns. So this would be around 200 microns maybe. So uh, this messy surface is what you have in this. So the changeover from this clean fatigue surface, striated fatigue surface, to this messy surface tells you that the crack grew by fatigue up to here, and then it grew catastrophically, and because this is a brittle material, it leads to this kind of a messy surface, which is a typical signature of brittle fracture, or it's also called cleavage fracture. So that tells you two things that we probably will not have time to discuss in this course. The two things are, why do uh, why do the initial defects exist? So I have given you some reasons that justify why these initial defects exist. And the second is the reading of fracture surfaces. So reading of fracture surfaces is a growing science, is a developing science, and now there are quantitative techniques available to read fracture surfaces, and a lot of work is being done in this area. So this is something that we are not going to cover in this course, but I wanted to give you a feel of the fact that just by looking at fracture surfaces, you can do a lot of post-mortem and try to tell what exactly caused the fracture. Not always, but many a time. One thing that we are going to keep in our mind and going to use quite a bit among the things that I talked to you about are these concepts of fracture based design. So these three concepts of fracture based design are going, we have to keep them in mind and put everything that we are going to do from now on in this perspective. Everything that we are going to do from now on is going to, we are going to shift gears in a big way, and things are going to be mathematical from now on. But we have to position these mathematical concepts in terms of the design ideas that uh, fracture mechanics offers us. These are alternate design ideas that fracture mechanics offers us, and we have to keep them in mind. So I'll end this lecture here. From in the next lecture, we will look at the elastic fields, elastic stress and strain and displacement fields in the at the front of, at the tip of our sharp crack. Let me stop here.